Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how work is calculated on a gas and how to draw PV diagrams. So what we're looking at here is some sort of piston cylinder assembly. These different colored dots in here are representing molecules of some sort. So there's some sort of gas in here. Now remember, in physics when we talk gas, we're not typically talking about gasoline. We're talking about things like air, nitrogen, helium, things of that nature. So imagine, we've got some sort of gas here. The different dots are representing possibly different types of atoms. All right, things to keep in mind, I've drawn like, maybe 30 some dots, but the actual number of molecules in this container, these are numbers like 10 to the 23rd power, 10 to the 24th power, that type of thing. All right, and imagine that this piston here is free to move. Now, if we want it to move, we're going to have to basically push on it, or in physics we would say, we're going to have to apply a force. So imagine that we do that. So we apply a force, in this direction to the right. And then imagine that the piston moves a small distance here. We're going to call that distance delta x. Now, when we calculate the work, right, work is force times distance, so that's going to be F times delta x. Now, we're going to think about this force a little bit. This force is related to one of the thermodynamic variables having to do with this gas. So hopefully you've seen my video on thermodynamic variables, but one of them is pressure. If I think about the variables in this container, we have a pressure, a volume, and a certain temperature here. And the pressure is what's making it so that we have to apply a force onto this piston. So what I'm going to do here is take a moment and draw a free body of our piston here. I'm going to go ahead and include this force we already put in there. Alright, so I'll do this down here. So a free body of this piston, we've got our applied force to the right. In addition to that, however, we have a force created by the molecules hitting this container, and that force is what's sometimes called a pressure force. And that force is going to be to the left. And that force is equal to pressure times the cross-sectional area of the piston. Right, this is coming right from how pressure is defined. Again, if you've seen my video about this, pressure is defined as force per unit area. So rearranging that slightly gives how pressure forces can be calculated. Now, as long as we're talking about moving this piston relatively slowly, then this is an equilibrium condition here. There's no MA term. So basically what we have is that, right here, I guess, the sum of all forces equals 0, right, positive. So we have the force that we're applying is equal to this force, which we can write as pressure times area. Right? So now if we go ahead and insert this term right here, here's what we have. Work is equal to force, which is pressure times area, times delta x. Right? Now, this product right here, area times delta x, that represents the change in volume of this gas. Now it's important to realize it's not the volume of the gas, it's the change in volume of the gas. So we can write this work term, work equals pressure times change in volume. And this is how work is typically calculated with gases. You'll notice if you work out the units, pressure is in Newton per square meter. Change in volume would be in cubic meter, and we end up with Newton meter out of this, or joules. Now, let's talk plus and minus signs. When I'm dealing with work, this is what I usually do. I usually just worry about magnitudes. So the magnitude of the work done is going to be the magnitude of this thing, pressure times change in volume. And we'll talk plus and minus signs later in the context of the first law of thermodynamics, but giving you a heads up of what's coming, there's a sign convention for when work is positive or negative, and that depends on whether you are talking in terms of work done on a gas or on a system, or work done by a gas. In all the videos and in all my classes, I always take the sign convention of work done on the system. So the work done on a system is positive when we compress this gas, because when we compress it, this force times this distance gives a positive value. And that's going to represent an energy transfer to the gas itself. And as a result of that, both the pressure and temperature will go up. So I'll just say this for sign convention that I'm going to take. The work is positive, or the work is greater than 0 when the gas is compressed. Right? Means, when the volume drops. Now, typically when you do work on a gas, the pressure changes. So this thing right here is not as easy to calculate as you might think. So what I'm going to do here is clean this up. Right. And because the pressure tends to change with the volume, it can sometimes be a tough math problem to calculate the work. So what we do is we use what are called PV diagrams. And here's what a PV diagram looks like. Right, just like its name implies, it is a plot of pressure against volume. Now, even though I just got done saying that usually the pressure is not constant, but just humor me and imagine for a moment that we do have a constant pressure example. And imagine that we have a gas that starts here, right, at a V1 and a P1. And let's imagine that that gas expands at constant volume. So if we do, expands at constant pressure. If we do, what that means is on this picture we'd be moving to the right, to some new volume, V2. Now, work is pressure, which in this case would be P1, times change in volume, which would be V2 minus V1 in this example. It's important to realize that pressure times change in volume is giving this distance times this distance. So what we're doing is we're calculating the area under this curve right here. So in other words, work is area under PV curve. Right, so PV diagrams are very handy for calculating work. Generally speaking, the work will be negative when we're expanding in volume and positive when we're compressing or decreasing in volume. So I think that's enough for this video. I'll go ahead and make examples of demonstrating these concepts with some numbers, but for now, important thing, for gases, work is pressure times change in volume. I usually just think in terms of magnitudes, at least for right now. And I like to think of the plus and minus signs conceptually. The work is positive when the volume is dropping, or in other words, when the gas is being compressed. And if you think about this in terms of what's happening to these variables, when you do positive work on the system, you're compressing the gas, the temperature and pressures go up. So when you're doing positive work, you're transferring energy to the system. And I think that's the more consistent sign convention with the way physics classes are typically taught, because when you're talking work terms on almost any system, typically they're positive when you're increasing the energy state of the system. All right, so our work is going to be positive when the volume drops. Work is going to be considered negative when the volume increases. So that's enough for now. Everybody have a great day.